Pluto is a faraway, mysterious, and prominent planet that was once considered part of our solar system. Despite recent groundbreaking assertions from prominent astrophysicists like Neil deGrasse Tyson and Michio Kaku, Pluto has been reintroduced into public discussion. They've suggested that the icy planet might be heading toward a possible course of collision with Neptune. However, how could such a situation exist, and what would the consequences be of such a historic event? Are we observing something unusual and unpredictable, a phenomenon, or is there something more to this impending cosmic disaster? Join us as we investigate the potential outcomes of a Pluto-Neptune collision. Pluto, which was once classified as a planet but later redefined as a dwarf planet, continues to be a subject of interest and investigation in the vast universe. Recent speculations from leading experts have suggested that Pluto's orbit is alarmingly close to Neptune's, prompting astrophysicists Neil deGrasse Tyson and Michio Kaku to warn of the possibility of a disastrous collision between these two celestial bodies, an event that could pose significant danger to Earth. But how could such a collision even occur? Pluto's orbit around the Sun is distinct from that of any other planet in our solar system. It takes an incredible 248 years to complete one full orbit, and since its discovery in 1930, Pluto has yet to finish a single revolution. However, the enchantment does not end there. Pluto is distinguished by its elliptical shape, which strays far from the nearly circular orbits of the major planets. Even more unusual is its tilt. Its orbit is inclined 17 degrees from the plane of the solar system. This gives Pluto's path a far more erratic trajectory compared to the more orderly orbits of the other planets, adding complexity to its orbital dynamics. Perhaps one of the most fascinating aspects of Pluto's orbit is where it comes into contact with Neptune's. For roughly 20 years during each orbit, Pluto actually gets closer to the Sun than Neptune does, defying the conventional expectation of their relative vantage points within the solar system. This raises the obvious question: why hasn't Pluto collided with Neptune? The answer lies in gravitational forces. After Pluto's discovery, astronomers quickly sought to understand its strange orbital behavior. Unlike the other planets, whose orbits are relatively close to the solar plane, Pluto's orbit stands out because of its steep inclination and highly irregular shape. As the mystery deepened, it became evident that Pluto's orbit crosses Neptune's. Despite this, their orbits remain stable, demonstrating the intricate mechanics of celestial dynamics, particularly the so-called three-body problem in space. Understanding how three objects like Pluto, Neptune, and the Sun interact gravitationally is key to this scenario. It's like trying to predict where these objects will be based on their starting points and mutual influences. The concept of non-concurrent libration helps explain this stability. In the case of Pluto and Neptune, this means that whenever Pluto crosses Neptune's orbit, the two bodies are always positioned at least 90 degrees apart. This spatial separation prevents a collision between them. Another contributing factor is orbital precession, which refers to the slow vertical movement of a planet's orbit. For Pluto, this means that when it comes closest to Neptune or any giant planet, it is positioned well above their orbital plane, providing yet another layer of defense against potential collisions. Another factor in play is VSK wobbling, a concept named after three researchers, Vokrulicki, Sidlichovsky, and Kaula, who studied how celestial bodies interact due to the gravitational pull of one another. This effect explains why Pluto's orbit, though seemingly chaotic, persists over extended periods of time. Pluto is influenced by both Neptune and the Sun, whose gravitational pull helps ensure that, despite its erratic shape, Pluto's orbit remains relatively smooth. VSK wobbling demonstrates that even in unpredictable environments, there are underlying patterns and forces that maintain equilibrium. This three-body problem is crucial to understanding the nature of Pluto's orbit, its relationship with Neptune, and the behavior of distant objects in our solar system. Numerical simulations carried out in the late 1980s revealed that despite stabilizing forces, Pluto's orbit is actually quite erratic. Small deviations in its initial conditions may result in significant differences in its path over centuries. Nevertheless, these simulations also demonstrated that Pluto's orbit remains stable over very long time scales, such as millions or even billions of years. To fully comprehend the dynamics between Pluto and Neptune, it's important to consider the gravitational influence of the giant outer planets, Neptune, Saturn, and Jupiter. Neptune's influence is significant, as it governs Pluto's orbit through a special resonance. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This gravitational resonance helps keep Pluto's orbit stable. But Neptune is not the only player in this complex equation. Jupiter's massive gravity also plays an important part in keeping Pluto's path steady, while Saturn further contributes to this dynamic. Interactions between these forces ensure that Pluto stays on a relatively steady course, possibly for millions of years, preventing it from posing any real threat due to Neptune's influence. Without these stabilizing forces, the solar system would be much more chaotic, with planets potentially colliding or being ejected from their orbits, triggering catastrophic consequences across the system. The possibility of Pluto colliding with Neptune in the future emphasizes the complexities of celestial mechanics and the importance of studying orbital stability. By understanding these intricate dynamics, we gain a better comprehension of how the solar system works, the role of gravitational forces, and the behavior of distant objects. Although Pluto's orbit may appear chaotic at first glance, it is a testimony to the delicate equilibrium of forces that keep it in place. Exploring space often leads to surprising discoveries, and Pluto's irregular orbit serves as a prime example of the mysteries of the cosmos. The concept of orbital chaos illustrates how a celestial body's orbit can be extremely sensitive to its initial position. In Pluto's case, even a tiny change in position or speed could drastically alter its long-term trajectory. Automated simulations have proven invaluable in helping scientists study these behaviors by modeling how Pluto and Neptune influence each other through gravitational forces. These simulations show how even the tiniest adjustments in initial conditions can have a significant impact on Pluto's trajectory. Though its orbit is stabilized by mechanisms like libration and precession, Pluto's path is far from constant. Minor variations in its early parameters may result in vastly different outcomes, making long-term predictions about its movement extremely challenging. Despite this apparent chaos, Pluto's orbit remains relatively stable over geological timescales, spanning billions of years. This suggests that even amid seeming disorder, there is an underlying order to Pluto's motion around the Sun. Predicting celestial movements, especially for objects with irregular orbits like Pluto, is a massive challenge. The inherent unpredictability of these systems means that long-term predictions are always. This intricate gravitational interplay reveals that the solar system is not a static, clockwork mechanism, but a dynamic and delicately balanced dance of celestial bodies. Pluto, despite being small and distant, plays a meaningful role in that cosmic choreography. Looking ahead, continued advancements in computational modeling and observational technology will enable scientists to refine their predictions about the future of Pluto's orbit and its interactions with other planetary bodies. Space observatories and missions, such as NASA's New Horizons, which provided our first close-up images of Pluto, are crucial to improving our understanding of such distant and complex systems. Moreover, what we learn from Pluto's chaotic yet stable orbit has implications that stretch far beyond our own solar system. The lessons drawn from these dynamics help astronomers better predict the behavior of exoplanets in distant star systems. Many of these exoplanets exist in multi-body systems where gravitational interactions can be even more unpredictable than those in our own neighborhood. In essence, Pluto becomes a case study, a distant, icy laboratory through which we test our theories of celestial motion, chaos theory, and orbital resonance. Its journey around the Sun is more than just a solitary voyage. It is a narrative woven into the fabric of cosmic evolution. As we continue to unlock the secrets of space, Pluto reminds us that even the smallest bodies can have the most profound impacts. Its peculiar orbit, its near collisions, and its reclassification all echo a larger truth. The universe is in constant motion, and understanding it requires a blend of observation, mathematics, curiosity, and imagination. So, will Pluto ever collide with Neptune? The answer, at least for now, appears to be no, thanks to the elegant dance of gravitational resonance, inclination, and cosmic timing. But its orbit will continue to evolve, and so will our models. As we explore deeper and further, the story of Pluto, like the universe itself, will continue to unfold, revealing new mysteries and challenging our understanding of the celestial mechanics that shape our cosmic home. Astronomers have expressed concerns regarding the possibility of Pluto and Neptune colliding, despite all the stabilizing forces at play. Neil deGrasse Tyson, a leading physicist and one of the individuals responsible for the reclassification of Pluto from a planet to a dwarf planet, offers an insightful perspective on the ongoing mysteries of our solar system, including Pluto's future. Tyson has played an important role in reshaping the public's perception of Pluto and in understanding its place within the evolving landscape of our solar system. Tyson doesn't see Pluto's reclassification as a loss, but as an essential adjustment based on our growing understanding of space and celestial bodies. Tyson's approach to celestial mechanics is one of constant discovery and evolution. He sees the complexities of orbits like Pluto's as indicative of how much more there is to learn about the universe. Although Tyson remains optimistic about the study of space, his views on Pluto's potential collision with Neptune suggest that numerous questions remain unanswered. Will Pluto encounter Neptune, or is this just a brief confusion in the universe's ever-changing state system? Only time and further research will provide the answers. For now, we are left with greater curiosity than before. How much is still unknown about our own solar system? The potential for a Pluto-Neptune collision invites further examination of the mysteries of the universe and the problems we face in understanding planetary dynamics. The prospect of two celestial bodies with vastly different properties colliding raises intriguing questions about how gravitational interactions shape the evolution of the solar system. A collision between Pluto and Neptune would not only have significant effects on our understanding of planetary behavior, but would also provide valuable insights into the evolution of the solar system itself. To understand the dynamics of a potential impact between Pluto and Neptune, it's essential to consider the characteristics of both planets. Pluto, though classified as a dwarf planet, contains a variety of elements and compounds in a frozen state, thanks to the extreme cold of the outer solar system. Its surface is covered with nitrogen ice, and its atmosphere is primarily composed of methane, nitrogen, and carbon monoxide. In contrast, Neptune, a massive gas giant, consists mainly of hydrogen, helium, and other lighter elements, with a deep, dense atmosphere. A collision between these two vastly different bodies would undoubtedly have a significant impact, conceivably triggering an event that could be seen from vast cosmic distances. However, it's important to note that Neptune's gravity is not the only stabilizing force in play. Jupiter, the largest planet in the solar system, also exerts a significant gravitational pull, contributing to the stable orbit of Pluto and preventing it from venturing too close to Neptune's domain. Saturn's gravitational influence further complicates the interactions in the outer solar system, which makes it unlikely that a devastating collision between Pluto and Neptune will occur. While Neptune's gravitational influence plays a significant part in maintaining Pluto's orbit, the complex relationships between other planets, such as Jupiter and Saturn, ensure that Pluto's path continues steadily. However, research has also shown that the connection between Pluto and Neptune is not as easy to navigate as it seems. A potential course of collision is avoided due to gravitational resonance between the two planets. Pluto orbits the Sun twice for every 3 orbits of Neptune, a relationship that creates a natural barrier preventing them from colliding. This resonance, often described as a gravitational dance, ensures that the orbits of Pluto and Neptune, while intersecting, never result in a collision. This mechanism is a remarkable example of how celestial bodies can maintain a harmonious relationship despite the tumultuous forces at play in space. Yet, the future of this delicate balance is not guaranteed. Small shifts in the relative positions or speeds of the planets could disrupt this resonance and lead to unpredictable consequences. These changes could be sparked by external forces, like the gravitational influence of an undiscovered planet or a passing star, or internal occurrences such as tidal forces, causing gradual changes in orbital behavior. Studies of these bodies' orbits continue, and Pluto, Neptune, and the surrounding bodies in the solar system's outermost regions remain crucial for understanding the long-term stability of their interactions. As technology advances, scientists will be able to improve their models and develop a clearer understanding of the dynamics between these distant objects. New information may shed light on the delicate balance that keeps Pluto and Neptune from colliding, or may uncover entirely new forces that could alter their relationship in the future. As we continue to study, one key aspect of Pluto and Neptune's dynamics that has emerged is the possibility of an undiscovered object influencing their orbits. This hypothetical body, frequently referred to as Planet 9, is believed to exist in the far reaches of the solar system. Some scientists have speculated that its gravitational pull could alter the orbits of objects like Pluto, potentially pointing them in new directions and destabilizing their current positions. While the existence of Planet 9 is still a subject of debate, its potential impact adds another layer of complexity to the situation. In addition to gravitational interactions between planets, it's crucial to think about the larger picture of how the solar system itself is evolving. The Sun, being the dominant gravitational force in the system, is gradually losing mass through the process of solar wind. As the Sun loses mass, the orbits of all the planets, including Pluto and Neptune, could slowly grow over time. This process could shift their relative positions and influence their long-term orbital stability. Furthermore, the outer solar system is not a static place. Objects like comets and other small bodies are constantly passing through, exerting their own gravitational forces. These passing objects could occasionally disrupt the orbits of distant planets, including Pluto, even though such occurrences are uncommon and improbable. Still, the combined impact of these diverse forces may ensure that Pluto's orbit remains dynamic, constantly adjusting in response to the gravitational dance occurring between worlds. On a more speculative note, the possibility of a large-scale event, such as the collision of two smaller objects in the far reaches of the solar system, could also contribute to the reversal of the trajectories of objects like Pluto. If such an event were to occur, it might trigger a chain reaction that could impact Pluto's path in ways we cannot currently predict. This highlights the chaotic nature of celestial dynamics, where even minor events can lead to large-scale changes over time. Understanding these potential scenarios requires advanced simulations and continuous observation. While we currently have a good grasp of Pluto's orbital behavior, the true nature of its course in the future will be determined by a multitude of factors that are difficult to foresee. The ongoing study of Pluto, Neptune, and the outer solar system remains a crucial aspect of modern astrophysics, offering insights into the forces that govern our cosmic neighborhood.